In this video, I'm going to show the image of why you need a current meter. From the white current source video, we've known the current accuracy is very important to provide a well-defined DC operating point for a current more large amplifier, including any circuitry. But how can we make it? Cool. We can implement the current source with an active transistor here. In addition, with the supply VDD, we could even arrange a resist divider to generate the required bias get to source voltage VGS for a current source. From the electronic 101, you've known the current voltage IV equation sets the transistor current. Do you see anything wrong with this equation? Correct. This current depends on the transistor threshold voltage VTH, which may vary from device to device, and we cannot make a well-defined current here. Therefore, the process variation would be an issue for the carrier mobility μ1, oxide capacitance per unit area C oxide, width, length, and threshold voltage in this equation. Also, inside the chip, the junction temperature would change over time, which would make the mobility and threshold voltage keep varying. Anything else? Yes, the VGS will indeed vary since the supply VDD may change. Apparently, this simple current source would not provide a precise current. What can we do? Think about your mirror images for 5 seconds. Bingo! We should apply a current meter if there is a precise current reference, like a bandgap current somewhere. We will talk about how to generate the bandgap current or R biasing reference later in another video. The current meter is to copy the precise current to any circuitry you need. From the two meter devices, as long as the two transistors are well matched, the process variation don't vary the copy current, since the current ratio will track each other. Similarly, both temperature and supply change will not change the meter ratio of the current. So, the current meter can copy the precise current everywhere on the chip. What's your current distribution images in your head? Right. This should be your current distributed image in every CML amplifier. In this arrangement, all the CML amplifier will receive all the precise current easily. Is this approach good enough? Be careful. The chip will be 5 mm by 5 mm or even bigger than that. What could be the issue? Think about the voltage drop image for 5 seconds. Correct. The voltage drop in the ground plane could be an issue. Remember, the ground wire should have a metal routing in the chip. Therefore, the final resistor with the current flow through it, the wire will cause the IR drop. As you can see, the ground voltage will be different between the left and the right hand side of the chip, even though the gate voltage of all the current sources is the same. The source ground voltage of all current sources are not the same. What's causing the issue? Correct. The voltage drop occurred since the voltage was distributed here. If that's the case, what can we improve it? Bingo! If the distributed voltage causes the voltage drop issue, why don't we just distribute current? Since current don't change between the source and the destination side no matter what. Correct? Again, with a good match current meter, the current can still be copied to any local place by the reference current in any local current meter for any local current source. In addition, The local current meter would reduce the change of routing congestion in the layout if lots of current needs to be sent to a great number of circuits in a multiple SerDes lanes. Therefore, the local current meter is very good to maintain the accuracy in a big chip current distribution. But what else could be an issue? Think about your current efficiency or power images for 5 seconds. Correct. The current consumption could be too big or wasted if the current ratio between the meters was 1:1. As you can see, we send those extra current meters just for distribution and do nothing for the amplifier's biasing. To reduce or save the current, you can not only apply the width ratio of both devices, but also keep a good current match in the current scaling. Besides the accuracy and efficiency, what else you should be careful about? Right. From the wide current source video, we've known the noise of the current source must be as small as possible for a Chromalogic logic amplifier. Unfortunately, the noise could be an issue with the current meter arrangement due to the applied current ratio. As you can see, the output current M times I ref would be metered by the input current. Similarly, the noise current would be metered by a factor of M. The total noise came from both the noise of both input and output current. Then, the current noise would be dominated by the big current ratio M. To make the noise multiplication under a reasonable number, we usually would not make the M bigger than 20, even though we prefer a big ratio M to reduce the power. This is the trade-off between the power and noise. What else we could do to reduce the noise further over frequencies? Think about the frequency-dependent component images for 5 seconds. Bingo! As we know, the current is defined by the gate to the source voltage VGS. If the gate to the source voltage has less variation, the current will vary less. Similarly, the noise is a kind of variation, and we could reduce the noise if we could reduce the VGS variation over frequencies by adding a bypass capacitor, which could reduce the impedance of the gate to the source over frequencies. Even though the bypass capacitor will reduce the noise of the current meter, we still cannot make the current ratio as big as possible. Why? Think about the gate linkage images for 5 seconds. Great. The transistor could have non-zero gate linkage, and that may still move the gate. Then, the linkage may still lead to a noise amplification at a big current ratio. Again, the current meter design exercise tells us there are trade-offs between the accuracy, power, noise, area, etc. As an analog designer, you may need to find a good balance between all the trade-offs. Here are the summarized images of why you need a current meter. To supply the precise current to all CMOS amplifiers or other circuitry as a well-defined bias in a big chip, the current meter is a must. In addition, to eliminate the voltage drop, we must distribute the current. Then, we need a local current meter to reference the precision current, and that also helps the current routing challenge in a big multiple lane SerDes layout. Even though the current ratio between the input and output current can be maximized to save power, the noise amplification and linkage could be a big concern in the noise performance. So, we suggest the current ratio to be under 20. To reduce the noise further over frequencies, we can add a bypass capacitor between the gate and the source of the current meter. But the area overhead could be a limitation. Lastly, the current meter design has all trade-offs between the accuracy, power, area, noise, etc. And you must optimize based on your system requirement. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with people who may be benefiting from it.